Okay, good morning. Welcome to
Family Math number 555.
FamilyMath 555. So our friend Suzanne van Ooy in an amazing Desmos program last night after you guys went to bed. And since I'm running out this morning, I thought we'd just take a look at it before I left. So do you remember the problem from yesterday?
Yeah, you have a square and you've got a line segment that you draw between two adjacent sides.
Uh-huh.
And the length of the line segment is 5.
Yep.
And the length of the square on the one side of the line segment is 13.
Okay. And what was the question?
Is this enough information to find the side length of the square?
Okay, and what did we learn?
We learned that it was not enough information to uniquely determine what the square was.
Okay.
Because we got a whole bunch of answers.
All right. But one of the things that was interesting was that we had a fairly complicated equation, and it would have been too difficult to determine exactly where that maximum was. But she's made a great program here, and I want to see if you can figure out where the maximum perimeter is. So just go ahead and just play with this. See what you think.
I can actually see it. It gets smaller as you move this down.
Okay.
It's up, bigger. You see it bigger as you go up like this, but then it gets smaller. I think the maximum is somewhere right around here. If I go too far down, it starts to shrink.
Uh-huh.
If I go too far up, it starts to shrink.
Okay.
Maybe like here-ish. And I guess that could be where this is an isosceles right triangle.
Okay. And why do you think that would be the case, that the maximum is where it's isosceles?
Well, I guess that's how you can get both of these sides to be as big. Both of these sides can be large at the same time.
Mm-hmm.
So, I mean, there's also a lot of symmetry. So both these sides can be pretty big. And then this is something, we don't know.
Yeah. And why do you think the symmetry is important?
Well, because normally you'd have something like this. We've got a really big piece here and a really small piece up here.
Okay.
But in our isosceles, they're the same. I'm not sure why that would help, but I think it does.
Okay. Well, let's see. So suppose this one was the maximum. Could you find another one? Another version of that triangle that would have where the square has the same perimeter as that one?
Yes.
Where?
Because it's where this side, I'm gonna pray, this looks sort of like that. Probably not exactly that, but...
Yeah, but down there, because there's another one of those down there. So if that one is going to be the same as the other one, as its, I don't know what to call it, it's not quite its mirror image, but its reflection maybe. And since we see this thing getting bigger, move it around so you can see the square getting bigger. It's possible the square could have been getting smaller, at which point the symmetry would have said it was the minimum. But the square's actually getting bigger and then shrinking.
Yeah.
So there's an argument, and we might have to check it, that the symmetric point that doesn't pair with anything is actually the maximum. Now, let me ask you one other question.
All right.
Without writing out the equations, we know that the thick black line is 13. What are the other side lengths? Or the side lengths of the right triangle?
It's 5 root 2 over 2.
5 root 2 over 2. So what's the total perimeter of the square here?
So it's 13 plus 5 root 2.
Okay. And root 2 is approximately what?
1.4.
1.4. So 1.4 times 5.
Well, it's 7.
Okay, and so that perimeter is,
So 20, which is right around what we thought it would be when we found the equation.
yeah. Now, is it bigger than 20 or less than 20?
It's going to be a little bigger than 20 because root 2 is a little bigger than 1.4.
Yeah, it's 1.414. So the perimeter here turns out to be right around 20. But it's actually a little bit bigger than 20, which is what we saw in our graph yesterday, although we saw that the side length was just a little bit bigger than 5. So there you go. So we could actually find the maximum by kind of this great geometry program and a symmetry argument. Good work, huh?